Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to provide an example of how to analyze a two-dimensional momentum problem. Now I've already did a little bit of the work in pictures in here to just save some time in the video here, but the idea is this, that a 500 kilogram cannon fires a 20 kilogram cannonball at 800 meters per second. And if the cannon is kind of free to roll and there's nothing holding it down, right? Hopefully it stands to reason that it would go rolling backwards, basically. And the first thing we're going to do is try to calculate the speed at which it rolls backwards. Now, let me talk about my pictures here. Okay, so what I'm calling position or state 1 here, I guess, is this. If you look carefully, I've actually put the cannonball right there. State 1 is before the cannonball has been launched. And take a note that there is no momentum in that picture, which is just fine. Okay, my state 2 here, right? Again, I've done better pictures, but humor me. The cannonball is now fired. It has a momentum vector equal to mass of the ball times velocity of the ball in picture 2. And it's fired at this 20-degree angle here that will be relevant in the problem, 20 degrees with the horizontal. And we would expect the cannon to be recoiling backwards. So this is my quick sketch of the cannon. We would expect it to be moving backwards and have a momentum that I called mass of the cannon times velocity of the cannon in picture 2. So I want to spend some time talking about what's happening while the cannonball is being accelerated down the barrel. So I'm talking about that, like 100th of a second, that the cannonball is changing velocity from 0 meters per second to 800 meters per second. Let's talk about that time frame. And this is my super duper rough picture of the cannon. Pretty much just drew the wheels because that's kind of all that's really relevant here. If we assume very small horizontal forces acting, right, then the impulse picture would look something like this. The mg is down and the normal would be up from the ground onto the cannon. Now I tacked delta t's on here just to make them impulses. If you wanted to just think of this as a free body diagram and ignore the delta t's, it's perfectly fine for this discussion here. All right, so this is basically a free body with just, times tacked on to make them impulses. And there's no reason to assume any sort of large impulse horizontally, but hopefully your gut will tell you this, that while the cannonball is being fired, this normal force right there would increase. So in this example, we would expect a net impulse in this direction. And you can kind of see that if we look at the pictures. Picture 1, nothing's moving, so there is no momentum in the y direction, right? X or y. But in picture 2 here, there is a momentum in the y direction because this guy, that animal right there, has a y component to it. And that means the system had an increase in momentum in the y direction. And this is where it's coming from. Those two vectors added together, right, during the time frame while the cannonball is being fired, this normal is larger than the gravitational force. So in this problem, the momentums are the same in this direction, but not in this direction. Okay, so that's enough on that. So moving on. Okay, so now if we write a conservation of momentum equation, con of mom in this direction, we'll call that way positive, right? The net momentum in picture 1, right, that's this picture. And remember, the cannonball is, in picture 1, is inside the cannon and not moving yet. So our total momentum is 0. And then in picture 2, our net momentum is the vector sum of the two momentum vectors in the horizontal direction. So this guy's magnitude is mass b times vb2. So mass b, vb2. but we need to multiply it by the cosine of 20 degrees because we only want the x component of this cannonball's momentum vector. And then the cannon, if it's moving backwards, now has a momentum to the left, so we'll go minus mass of the cannon times velocity of the cannon in picture 2. No sines or cosines required because this thing basically is directly opposite of the direction we call positive. And we can put the equality because of our discussion over here. There's no net force horizontally on the cannon, or even if there is, I don't see any reason to think it would be very large to affect it, you know, over the small time frame here, the small delta t over which this is happening. So now that allows us to write this equation and just put in the values, right? So I'm just going to skip the algebra step here and leave that to the viewer here, right? But, all right, 20 kilograms for this animal, 800 meter per second, cosine of 20 degrees, 500 kilogram cannon. Put those values in and solve for the velocity of the cannon in picture 2, and I got 30 meter per second. So the velocity of the cannon in picture 2 is 30 meter per second to the left. Now a little discussion of plus and minus signs. When you algebraically solve this for this variable, you will get a positive value. That does not mean that the cannon is moving to the right. What it means is your assumed direction is correct. So I drew this momentum vector and hence the velocity vector to the left. This came out positive, and what that means is it's in the correct direction in my picture. All right, moving along. Find the average horizontal force on the cannon if it rolls 5 meters backwards after firing. So this cannon now rolls back to here. I'm just going to use a dot here for the cannon. I don't feel like sketching it. I'm going to call that picture 3. This distance is the 5 meters. So in order to change this velocity from 30 meter per second to 0, there had to be a force to the right acting on that cannon. And that's what this problem is asking about, the average horizontal force on the cannon while it's rolling backwards 5 meters. Now, what is the nature of that force? Well, if this is like soft ground or something, that would give you kind of a combination of different types of forces there. Some could argue frictional forces. If you look carefully, like the normal force on the wheel is kind of like this way, and that has a horizontal component to it. The nature, the specific nature of where that force is coming from is not important for this question. Suffice to say, there must be a horizontal force to the right. Otherwise, this 30 meter per second would stay constant, and it didn't. So we can get at that force a couple different ways. What I'm going to do is write out a work energy theorem for the cannon. And let's call this potential energy 2 plus kinetic energy 2 plus all the work done on the cannon between pictures 2 and 3 is equal to potential energy 3 plus kinetic energy 3. And I'll put over here, this is for the cannon only. All right. So what we can do about the potential energies is this. We can just datum them out. If we put a datum right through here, then both potential energies are 0. Oops. So 0, 0. Okay. KE2 is going to be 1/2 mass of the cannon, velocity of the cannon in picture 2 squared. I'll do the work term last. I always do that. Kinetic energy 3 is 0 because the cannon is now stopped here at this position. And the work done, right, is going to be this force times the distance of 5 meters. Oops, sorry about that. So we're going to have force times distance, and that work term is negative because of the sign convention for work. The work is considered positive when the force is in the same direction as the velocity. It is considered negative when the force is in the opposite direction of the velocity, as is the case here. Darn it, I wish this wouldn't jump around like that. Okay, so that's why that work term is negative. And here's our equal sign. And I'll let you folks fill in the numbers. All right, the distance stated is 5 meters. The mass of the cannon is 800 kilograms. The velocity of the cannon in picture 2 is 30 meters per second. And if you put all those values in, I get a force of 72,000 newtons to the right. So that would be the average horizontal force acting on the cannon. I hope that this video helps you understand how to analyze two-dimensional problems using both momentum and work energy as appropriate. Have a great day.